very disorienting. Yeah, I think we're 2 minutes over, so it's time to start our next session. I'm really, really excited to introduce our next speakers. We have the Lean 4 team, Leo de Moura and Sebastian Ullrich, who are going to give us the latest and greatest news about Lean 4. So Leo has put in a tremendous and an incomprehensible amount of effort and energy and time into developing Lean, starting from the beginning, from 0.1. And it's clear that this meeting, this community, just like wouldn't be here. We wouldn't be meeting today without all of his incredible work. So if you're like me, recently you've been watching the news ticker, the RSS feed on Zulip, all the new commits, the Lean 4 repository, and today the big one came. There is now a milestone release of Lean 4.0.0. So yeah, it's time. Yeah, round of applause for sure. I'm not going to steal any more of Leo's thunder. Let's hear from Leo himself. So thank you, Leo. It's great to have you here.
Oh, great, great. Thank you. Can you hear me? Okay, great. We'd like to start thanking people that help us. Daniel Selson helped us with the type-class resolution. He gave a lot of feedback, participated in many design discussions. Mark and Wojciech developed the Lean server. It started working a few days ago. I mean, it's like last week. It was working. It's a big step forward, the Lean server. I started using for developing Lean itself, and now the feedback is instantaneous. We also like to thank Joe Hendricks, Andrew Kentz, Rob Dawkins, Simon Winwood from Galois Incorporation. They were early adopters. They're always giving feedback, suggestions, and using Lean 4. They have been using Lean 4 for a while. We also like to thank Dan Lyon, Simon Peyton-Jones, Nikhil Swani. They are all my colleagues and friends from Microsoft. But Sebastian also, there's the other Sebastian Graf and Max from Sebastian's institution. They also help a lot with design discussions, feedback, suggestions. Sebastian Graf is one of Haskell developers. Simon Peyton-Jones, everybody knows, is a Haskell developer. They are all super helpful. How did we get here? How Lean started. The previous project was Z3, is a push button to improver. Z3 was and still is used in many systems like F-Star, Daphne, that built by colleagues of mine, Isabel. To a very small extent, it's using Coq, right? Some people build bridges, but I don't think it ever became mainstream plugin like in Isabel. But in particular in Daphne and F-Star, there's always this loss in translation issue, proof instability issues because of the push button prover. We started Lean projects. The goal is to have Lean as a better Z3 for this kind of application. Z3 was very successful for test case generation, finding bugs as a constraint solving problems. But we want to make Lean like, let's try to make something that would be better for Daphne, F-Star, that instead of being first order logic, we can do higher order logic. The issues, we have support for interactive proofs too, would be like a library. But this goal never really worked. I mean, each one of the systems have very tiny differences. The foundations are different. Even in Coq, in the end, we start using Coq's foundation for Lean. Even connecting Lean Coq is not trivial, right? The 1.0, Lean 1.0 is just an experiment for learning dependence type theory. It's not very usable, actually. Rob, I think, uses. Jeremy, for sure. Jeremy Navigado, for sure, uses. Code Rule uses, but 4 is also used. I mean, is heroic use mode here because it was horrible. The first release was 2.0. We had an extension language for Lin 2.0 was Lua. Nobody ever used it. In Lin 3, I think the big thing is that people could start using Lin to extend itself. We saw, for instance, Ed gave this really nice talk showing how he used Lin programming capabilities for extending Lin, showing these widgets. And Lin 4, but at this point, Lin 3 reaches a point that is the limit of its design, right? It was not built originally for being an interactive system. We start patching, gluing things together to make it an interactive system, but we were hitting many brick walls. In 2018, Sebastian and I started developing Lin 4. Is basically is the biggest transition ever. From Lin 1 to 2 is big, 2 to 3 is big, but now it's gigantic. It's almost rebuilt everything again. But in Lin itself now, the main goal is to make sure that all subsystems can be extended by the user, can be modified. One thing that we like to tell people keep asking us, oh, is Lin a product? Is Lin going to keep changing? The main issue is that there's no spec. We don't really know what Lin should do. We try ideas, some of the ideas work, some don't, and you have to fix. And sometimes the ideas that we think they didn't work, some users think they work great. I will give some examples today. But in Lin 4, we really want Lin to be an extensible programming language, not just a tree improver. We want it to be a workbench for developing custom automation, domain-specific languages, software verification, and also formalized mathematics. We didn't forget the Mathly crowd. How did we do it? I mean, the first a common question people ask us is, oh, come on, the calculus of constructions, all functions are total. You can really build Lin in Lin itself, right? You want general recursion, you want foreign functions, you want unsafe features. Okay, the first thing we do is, we add unsafe keywords for people that are familiar with Lin 3. This is like the meta. The unsafe functions may not terminate. They can use unsafe features like unsafe typecasting, but they are completely sealed like the meta keywords. But the one problem with the meta keyword is that it's like a virus. It spreads all over the place. After you start using meta, you can't leave the meta words. This is very inconvenient when you're programming. Sometimes there are things that you want to use meta things, but you still want to reason about this thing you're writing. You want to seal the meta words. Okay, in Lin 4, this is the compromise we have. We can seal unsafe things. We can do that whenever the type, you have some constants that is implemented using unsafe features. If the type of this constant is inhabited, right, you are fine, right? You cannot compromise the logical consistency of your system by sealing it. You have these inhabited constants. You know this inhabited. The system will guarantee that's the only thing you know about it. I mean, you are not learning anything new, right? You're just giving a name to something that you know it's inhabited, a type that you know it's inhabited. And we use it all the time. You use for things that's implemented in C, like this Lin #64. Sometimes you have something's unsafe, but you want to implement in Lin because you want to rely on code specialization, inlining, many features you have in the Lin compiler, but you're exploiting information about the Lin runtime system, right? That cannot be even expressed in Lin itself. And you have this unsafe implementation that you know that's, for instance, here I'm putting some condition that guarantees that because I know how the runtime works, and this condition here guarantees that it is safe. I'm telling you, this is safe, and I'm going to seal it here. We do that many different places, but one thing that I want to stress If you're using Lean as a tree improver, the logical consistency is preserved. We will never allow you to prove false using this mechanism. Lean 4, in Lean 4, right, this was one of the biggest challenges. I tried to find a picture that reflects how complicated it is. When Sebastian and I started, we knew it was going to be hard, but it was way, way harder than we expected. We started by removing every unnecessary feature. We had like a Lean tree bare bones because we would have to keep changing it while we are developing Lean 4. This is like a Lean tree 0.5. Bare bones, there's no IDE support. I mean, we never get error messages in the right place. Basically, the granularity is, oh, it's in this function, there's an error. Here's the message. You have to figure out where it is. But in 2018, we had nice milestones. One was like Dan Lyons, a colleague of mine, is one of my heroes. He developed, we started explaining to him the Lean project, why the complications, and he starts helping us design a memory manager. He came up with really cool ideas on how to allocate memory for in a system like Lean. And we have this Mimalog system now. He developed Mimalog. Mimalog has a bunch of new ideas. The cool thing about Mimalog is a memory manager that you can, it's so small that you can implement your own version that's customized for your system. And we did that for Lean. This is the first performance boost. You may want to ask, what's this image here? This is a game that uses this Mimalog. Mimalog is not, there's one thing in common between video games now and Lean is that they use a similar memory manager. And that's not just that. Mimalog then managed to put Mimalog in many servers at Microsoft, reduce latency is a big thing. We started also the compiler, the new intermediate representation. The first parsing prototype, the first parsing engine we have for Lean was not very encouraging to parse core.lean. It took 56 seconds, allocated like 200 million objects. Is putting in our face the limitations of the tree Lean interpreter and system. After this first experiment here, 2 weeks later, with the code specializer of the new compiler reduced to 5 seconds, it's still horrible, but almost more than 10 times faster. Then we continue working on the codes, on the compiler, the code specialization engine, the simplifier. It's a very complicated beast. One thing I see all the time, people saying Lean compiler is a transpiler. It's not a transpiler. Come on, this is to the point of being offensive. Transpiler is when you map language A to B and they have the same abstraction level. It's like we're mapping C# to Java. They have the same abstraction level. Going from Lean to C is a brutal level. The translation is not trivial at all. There are many steps that you have to perform to get good performance. And Sebastian and I had this paper on showing how you can have destructive updates in pure code. In the beginning of 2019, we started getting really encouraging results. Like we had many benchmarks that we wrote in Lean, Haskell, compiled JDC, or Camel, and many others, but the most known ones are JDC and Camel, and Lean beats all of them. This is like the first version of our compiler was already outperforming Haskell and Camel compilers using this new technique we use. Dan Lyon came with this cool name, FBIP, that is functional but in place for this idea. It just changes the way you write programs, right? Functional pure programs, right? Because you can get structured updates, you can have hash tables and arrays, right? It is dramatic. I will show an example of how we change the way we write things. Some people try to use linear type systems, but they never pick up to get the structured updates in a pure setting because it's all or nothing. Here is much more dynamic. The counting immutable beans paper that Sebastian and I wrote And his collaborators implemented this technique in Coca, and they managed to produce all experimental results we had. They managed to reproduce. Now there are two systems that use this approach, Coca and Lean. Lean, for instance, one example, the Lean 4 red-black trees outperformed non-persistent version of C++. Non-persistent is that the user is doing destructive updates and you cannot share the tree, right? Because you're doing destructive updates there. The Lean is a persistent version. It outperforms, although it's not doing destructive updates directly, the user is not controlling them, and it outperforms C++. And the Coca does the same thing. After he implemented these counter-immutable beans ideas, they also managed to outperform the C++ version. And you may ask, oh, in the persistent version of red-black trees in C++, Lean 3 has this implemented, right? Yeah, it's like 10 times faster. I mean, if you go to the C++ red-black tree implemented in Lean 3, you compare with the one implemented in Lean 4, if you benchmark them, it's almost 10 times faster, the Lean 4 version. You may say, oh, you're generating C codes. I mean, you could do by hand. No, that's what we don't manage to convey this. Only when you see the generated code, you see nobody can write this by hand. It's too complicated. Then Lion is way better delivering this to the programming language community than I'm not a programming language person. He talks their language. He knows how to get them excited about this. And we were super happy that they have our algorithms in Coca now. The parser. Then after we started using, the first parser was too slow. Then our second version is say, let's try to use the functional but-in-place approach to design a new parser. Right, and using the new compiler that's now generating C code. Now we could pass core.lean in 20 milliseconds. He's just showing the parser states is a structure where you have an array, and I'm using it in pure code, this array. If you're programming Haskell, you would never do that, because if you're using an array, whenever you add elements of an array, you would be creating a new copy of the array. You would probably use a list, because you don't want to keep creating a new copy of the array every time. But in Lean here, the structural updates are happening behind the scene, right? And a reason of this 20 milliseconds is that we're exploiting the functional but-in-place idiom here. Type class resolution. This is another thing that's, we did a few experiments on type classes. That's we identified 3 big limitations in the Lean 3 type class system. The way it handles diamonds. Diamonds, what is a diamond is this phenomenon here. You have like a comonoid is a monoid and a com semi-group. And both monoid and com semi-group are semi-groups, right? The only difference here is one diamond. If you go to mathlib, you have like hundreds. I don't know. I mean, you keep making it bigger and bigger, the number of structures. I have no idea how many you have now, but you have a lot of them. Cycles, users sometimes create cycles by accident. Sometimes they are nice to have, but you can do it in the Lean 3 type class. Well, you can, but the performance is going to be really bad. And naive indexing was another problem. One thing I want to emphasize, there's no ban on diamonds in Lean 3 or Lean 4, right? Sometimes I see discussions like that. I don't follow all the discussions, but I've seen this kind of statement being made. And we have a new algorithm. Daniel worked with us on this algorithm that we call table type class resolution. It's based on an approach called table resolution. And it addresses the first 2 issues. And the third issue we address with better indexing that is friendly to dependence type theory. Dependent type theory creates many problems for indexing because most users are going to expect matching modulo the reduction rules of dependence type theory. And the discrimination tree, we also start using for everything in Lean 4, for unification hints, for simple lemmas, and so The extends, Link3 has this old structure commands that generate flat structures. They do not scale well. I mean, but this is the kind of thing that we tried. We know it doesn't work, but people love this. Some people love this feature. They think this is a feature. But we will always keep having problems. I see people creating shortcuts in their hierarchy because maybe they don't know it, but it's because of these flat structures. In Link3, you have a new structure, but very few people, I think, using mathlib. I'm not sure. In Link4, we have only the new structure that's produced a much more efficient representation that you can guarantee that you can move in this hierarchy very efficiently. Again, there's no ban on diamonds. The difference of the two commands, the Link3 old structure command and the Link3 new and Link4, is that you get only the blue, the fast paths, you get for free. The extra path here, you build manually if you want. That's the only difference. You may say, oh, this is not convenient. It's great to get this red path automatically. Yes, you can automate. If you want, you can automate generation of this path, but it should not be a flat here. Because when I build by hands, I'm using the common ancestor. I mean, here I'm not showing the whole hierarchy in this picture here, but you can get the common ancestor. You can make it much better than flattening all fields. You may say, oh, there are so few fields here. What's the big deal? No, no, no. For your structures in mathlib, you have hundreds of fields sometimes when you flat, right? And each step moving this hierarchy gets 100. You go to 95, then to 90, 80, and you keep packing in and packing. It's super inefficient, right? The elaborator. A few months ago, we managed to finally move to the new front ends. Basically in 2020, we spent, it was the year of the elaborator. We spent building the elaborator and all auxiliary modules like the static framework, dependency pattern matching, structural recursion, and so on. And finally, after almost 3 years, we managed to move to the new front ends. After a few weeks, the Galois folks managed to convert their tool to the new front end. We thought it was going to be a nightmare, but they managed to do it very quickly. These guys are from a different world. I mean, I thought they were going to kill us because the new front end has many backwards. They were already using Link4, but they are not using Link3. They were using Link4 old front ends that was implemented in C++ and shared many things with the Link3 front ends. And there were so many backwards compatibility issues, but they managed to do everything convert. And they got a performance boost. That's also another cool thing. Now, after that, we barely write C++ anymore. I think only when you have to fix some bug in the runtime, we had to do that. Fix bugs, they are everywhere. We fix bugs in C++, but all development now is done in Lean itself. I'm going to start flashing some things, some features of Link4. I will not go into detail, because otherwise I'm going to run out of time, but just showing some features, right? So like, oh, this is how you declare a new syntax, right? So you have a GSL for describing a domain-specific language for writing your own syntax. Here's how you define the subtype notation you are used to, that you have been using in Link3. How you define it, how you expand it in Link4. One cool thing is that you have many different syntax categories. It's not just terms. Like in Link3, basically, you can extend the language of terms. Here, you can extend the language of statics. You have terms, you have levels, you have syntax itself. You have the category STX. That's the category of syntax. This GSL for describe, you can use syntax to extend the syntax language. Right. For instance, here we are saying that STX plus is a new notation. What's the STX plus? Is the many one, right? When you want to create a parser that is going to try P one or more times, right? That you can use now STX plus. And you can create your own categories. like here, you're defining the index category, right? That you can use to index big operators. Your macros can be recursive, right? Here's I'm not going to go into details what it does, but it's a list here. You have a notation for creating lists that you have a bunch of elements followed by a list, right? They are all separated by commas. And here what we're going to do is say, oh, if the x is less than 8, I'm going to expand in a bunch of list conses, right? So I'm consing the elements. Oh, if it's greater than 8, I'm going to divide this array here in 2, get the first half, convert the first half and the second half, and put them together. Note when in my anti-quotation, we're using Y, there's no risk of name capture because the system is hygienic. That's what we mean by hygiene, that you cannot have accidental name captures. To put in context, this A bug I've seen people talking about is an example of unhygiene issue. You have an accidental name capture there. In Lean 4, there is zero unless you can always say, I'm not going to use hygiene. You can work around hygiene system, but if you keep using it, this will never happen. Most Lean tree tactics are just macros. And here's the funX tactic that you can, it's just to apply the funX theorem. Right here, I'm showing it in action. That I'm saying funX. Notice that I'm using patterns here already, right? I'm combining funX with intro, and intro uses the match static that uses the term match, and they are all macros, right? They are just expanding. FunX here is going to expand and apply the lemma, the theorem funX, use an intro, and then call funX, the text funX again. Right. The intro here is going to take care of this pattern matching here. And how it does it, it's expanding into the match tactic that expands in the term tactic, the term expression with a refine there. Another advantage of this approach is that you get a coherent system. If I change the match term, automatically this change is propagated through all these components that rely on this match term. In Lean 4, there's no built-in begin-end tactic block. We don't like it, but we realize some users love these blocks. And we say, oh, I like my blocks. Well, you can write a macro. It's just one line to get your begin-end blocks. You say you have a macro that starts with begin. It's a bunch of tactics separated by commas and ends with ends. This notation here is to copy the position information of your ends to the curly brace here. We do that in such a way. The goal here is to get the error message. If you didn't close, if you still have goals, you're going to get an error message in the ends token. Then you may ask, I like the trailing comma. I've seen people talking about this stuff. I want my dangling comma there. No problem, you can change your macro. You can put a comma, question mark. You have now optional comma there, and you can have the comma you love in the ends. Some people, for me, these things are like noise, like how you write functional application. But I've seen even hardcore developers, they hate the way we write functional application, like F space A space B space C. They like to write functional application like that, like in Java or JavaScript. Yeah, you can declare this notation, right? And you can use, here's a good example of using white space sensitivity. You can say term, no white space, parentheses, a term followed, a bunch of terms separated by commas, close parentheses. And this is how you expand. You're expanding this functional application with parentheses, you're expanding the default one, and now you can write F parentheses 1, 2. You may ask, why do you have this no white space? It's to address ambiguity, right? Because you could view F space parentheses 1, 2 as the function that takes a pair, right? String interpolation, this started as an example. We wrote this. You don't need to be a Lean developer to add this feature. Now we add it to Lean because it's so useful, but it started as an example that you could extend the parser, the elaborator, however, you could do everything outside of Lean. As a user, you could add this feature. And string interpolation is just a convenience, but it's a big convenience, allow you to create messages like instead of writing X, the string X column concatenated with two string X, concatenated with this string, concatenated with two string Y, you can write this very compact version. And this was so successful, we use that everywhere. We even have an interpolated str construct that is a parser, it's a parametric parser. You may say, what's the parser you want to use inside of the curly braces? Usually it's a term, but you can use whatever you want, right? And we're using Lean for generating error messages. It's used everywhere. Do notation is another example of GSL. You don't need to be a Lean developer to implement this notation, but we did it because it's super convenient for us. Daniel was one that was always complaining about the do notation, saying that I prefer to use imperative languages. This do notation sucks. But it's better than writing the binds by hand. This was introduced by Haskell. It's way better to write, at least in my point of view, to write the do notation than write the binds manually, right? But in Lean, we have the do notation like in Lean 3, but you have many extensions. I will go over some of them. For instance, you can have support for iteration and mutable variables. There's no destructive update. This is just a convenience. This is a fold that you're carrying the S here. This becomes a fold, right? But it's much more convenient to write like that. And we do that all the time in Lean, when we are developing Lean itself. You have a return like in Rust, right? That's here you're returning from the block, the whole you're returning from the, in Rust you return the function, but here we return this do block. We are saying, oh, this is the result of this do block here. Here's a point that's showing that we use to implement Lean itself, the do notation. It's so more convenient than using folds, packing pairs. For instance, here I have muting two variables. You can do that. It's so smooth, the experience. Daniel was right when he says that this is horrible to do in functional programming. This is one place where functional programming is not as convenient as imperative, but we fix that with the do notation. And you can extend it if you want. You can write your own. This can all be implemented outside of the system. Another thing that's for people that are using many different monads. Here I have a monad M with the two effects, except in state. I have a monad N that extends the monad M with more effects. This is always annoying when you have different monads in the same code. Like here, deposit is in the monad N, and if you draw in the monad M, in Lean 4, you have auto-lifting. It's like a coercion for lifting between monadic words. And say it's not a big deal, but the comfort you get is dramatic. And now before that, it was really painful to work with different monads. Now it's super smooth for us. And we have nested actions also, like one nasty thing about monadic code is where get is an action. Sometimes you want to use the result of the get in a condition. You have to do some like, create this temporary variable. No, in Lean 4, you can have nested actions. It's just a macro. It's going to expand exactly what is here. It's going to lift this stuff and add the latch for you automatically. It also makes the code very comfortable to write. Let's talk about the task framework. Now everything is structured. We try to emphasize, because now we have a very expressive language to define the syntax, not just of our terms for our tactics and everything. You can you can have a much richer language in the tactic framework. For instance, almost all our tactics are structured like induction cases. You have match, right? Yes, you have all the power of dependence pattern matching in tactic modes. This is not a refine, right? You see the right-hand side is a tactic. I'm not leaving tactic modes, going to thermal modes and going back. This is all behind the scenes. This is happening behind the scenes. Exactly as I said, the match with works in tactic modes, right? You can have patterns, you can have patterns of patterns and several arguments. And this is super smooth. Notice that I'm in tactic mode, or the by here is switching to tactic mode. Another thing that we have is multi-target induction. Is useful when you have your own custom induction principles. Like here you have an induction principle for the modulus operation that has two targets, X and Y. And you can do induction with this kind of induction principle, right? And still have the structure. You don't have, you see that I'm saying, this is the int case, this is the base case, the names are come from the parameter names, and you can provide them in any order. You don't have to follow the order they were defined as. I think this makes your tactic scripts much more robust. Another thing that we are trying, but for sure some people will hate, is that we, by default, you can't use names that were generated by tactics. For instance, here, I put an underscore here. The intro tactic is going to create a name for this new hypothesis. In this case, it's A1. You can't use A1. You get an error saying this is inaccessible. You have a notion of an inaccessible variable. When you see your state, you're going to see you have like a tombstone that marks variables that are inaccessible. You can't use them to write proofs. When you are saying that you don't want to give naming to something, it means that you have to close your proof without using the name of the hypothesis, like saying assumption here. But you can disable. We realize some people will not like this feature, and you can disable by saying hygienic intro false, and now you can do whatever you want with these names. I mean, in my point of view, your scripts are going to not be very robust because they are relying on auto-generated names, but that's fine. Now, Lean for Simp. One of the major bottlenecks in Lean 3 is Simp. Daniel had some heroic efforts profiling mathlib in the end of 2019. Here's some of his findings. There are 15 million Simp failures in mathlib. I mean, mathlib in 2000 probably is 100 million now, but in 2019 was 15. Failure here means you try to use a lemma, it doesn't work. You did that 15 million times to compile mathlib in 2019. The problem that is in the lack of indexing. Another problem is that the Simp set is being reconstructed all the time. This one's probably fixable in Lean 3. The second one is hard. Lean 3 uses the keyed matching approach that Georges Gontier came up when he was doing math comp. Key matching works great for what Georges does. He does his proofs using he writes only. He likes to have total control over his proofs. It's like saying he writes using this lemma. He expects this lemma is going to succeed. It's like you're not trying something that may fail. He write tactics that Georges tries, they succeed. There are very few failures. Maybe he may try he write in the wrong place until he gets the right place, but there are very few failures. Simp is the opposite. You have a collection of lemmas, right? Big set of lemmas, and you're going to try. Most of them are not applicable to your goal, and you keep trying. Then you got statistics for the lemmas. For instance, this one here was tried more than 36,000 times, and none of them succeeded. The problem here is like you have the left-hand side of this lemma is this term here. The key match is saying that I'm going to try to apply this lemma whenever you have an equality. Yes, you have a bunch of equalities in mathlib. You're going to try every place where you have equality and you say simp, you're going to try this lemma. That's why you have 36,000 failures. And the other ones are very similar, right? There are thousands and there's a bunch of these lemmas, right? And okay, let's use indexing, better indexing, but indexing that is customized to dependency type theory. And let's see if we can expose. I mean, we can't read mathlib in Lin4, but you can try to create a benchmark, a crafted benchmark that exposes the problem. For this one crafted benchmark is this one here. I have f of g1 of x is equals to f of g0. And I keep doing this chain up to f of g for 499x is f of g of 498. And then I try to prove that f of g of 0x is equals to f of g of 499x. Here's the number of lemmas. You can keep creating this benchmark for different ends, right? I create for 500s, 1,000, 1,500, and so on. And these are the times of Lin3 and Lin4. Lin3 is trying to apply these lemmas in sequence, right? Because the key is f, right? So it's going to try, and you get exactly quadratic behavior. If you see this exactly x squared divided by 2, what is happening here. And Lin4 is essentially linear time because it has better indexing. He goes to the right lemma every single time. He tries only once. This is an example that you can, first here you have 3,000 lemmas, right? And you applied, to prove the theorem, you applied them 3,000 times. And in Lin4 did that in 1 second, a little bit more than 1 second. The match width, there are many improvements in the match width compiler. This was a big thing. The first thing to keep in mind, there's no equation compiler in Lin4. The termination checking, how you show to the kernel that something terminates and how you do dependent pattern match are completely decoupled now. Actually, this notation here is syntax sugar for this one. We expand into a match. And for each match expression, we create a matcher. It's an auxiliary function. That's independent of the right-hand side. It has a motive, and this motive has the number of discriminants you have, AS and I. And you have one parameter. You can do as a minor premise for each alternative. The first cool thing about this stuff that's it allows you to change the motive. When you're going to show that something terminates later, you can add extra arguments. Like here, I'm using the list below for people that are familiar with this structure, how we prove that something terminates using structural recursion in Lin3. You get this list direct home, and you have to add this below arguments there. And since my motive there is an argument that I provide, I stick my below there. And it will be refined in each alternative. That's exactly what you want. One cool thing that this match hides all the nasty details, and you get a really nice split printing of the match expression. This is the kernel. We sent a kernel, we compiled erase IDX, sent to the kernel, and here we are printing the result back. And you see that you see the match expression there. You see 3 alternatives exactly as you wrote here. We also preserve information about inaccessible elements, like here. This underscore here is an accessible pattern. This is the notation for inaccessible patterns, like in Lin3. It's f of a, what is there. If you have named patterns, this is also preserved when you print. You may think it's not a big deal, but if you're doing software verification, you have matches all over the place, and it's really nice to see the match expressions in your goals. We also have this extra goodie. Now you can have H column to have H is a proof that A equals true in the first branch, and a proof that A equals false in the second branch. In Lin3, you have an idiom for doing that, where you have to pass a raffle. It's so annoying. I always forget how you do I have to search how you do it. Now it's super convenient. There were many bugs in the Lin3 dependent pattern matching. engine. Daniel was the first one to report the bug, but the bug was discovered many times. These bugs were fixed in Lean 4. Recursion, as I said, it separates. You have basically, you have neutral blocks, you have let's rec, you can have local recursive functions. We view the let's recs, they are lifted by the elaborator. You have like a huge neutral block that we compute strongly connected components, separates them. And each component you can solve using one of these strategies. The simplest ones, the element is not recursive. You can have structural recursion, unsafe, and partial. Partial is not as, partial is like unsafe, but you can only do general recursion. You cannot use unsafe functions in partial. And well-founded, that's work in progress. We didn't finish well-founded yet. The let's rec is super useful, no auxiliary definitions. I mean, before, it's like, oh, I want to add this function, but I have to create an auxiliary function for doing structural recursion there. No, you can have a let's rec and you use add here, it works. You may say, oh, I don't care about programming. You can use let's rec in proofs too. It's super useful. You can do let's rec for just like auxiliary induction, proof by induction. You can have many, for instance, this example here, 3A cyclic, has like 3 nested let's recs there. And you have your inductions, you write them as you're writing recursive functions, everything works. We have where clauses that expand into a let's rec. It's like the Haskell. I now prefer the where than the let's rec. I think they look nicer. In my code, I use where all the time. And for proofs, same thing. The same way, I wrote this example before we had the where, but probably it is much nicer with the where. Elaborate. I'm going to flash some features of the new elaborator. Like we have named arguments. I think this is super useful. For instance, you can, if a programming fold is really nice one to use with named arguments, but for people that care about proving, it's really nice when you have to provide the motive. For instance, you have EQ subst. In Lean 3, if you want to provide the motive explicitly because the elaborator couldn't infer it, you have to put an at here, a bunch of underscores. I always forget how many underscores you need. I don't remember. For me, EQ subs has 2 arguments and the motive. The rest doesn't matter, right? And with named arguments, it's really convenient. You can provide an implicit argument, right? It's much easier to read. I think, for me at least, I never remember the number of underscores, which one is the motive. And now this is much nicer to use. Another feature that's drove me crazy in Lean 3 is that you have very limited support for postponing the elaboration of terms, in particular when the term is nested inside of a binder. Here's a common example. You would want to use the dot notation, but since I don't know that R is a list in Lean 3 at this point, only later when I get here, that I know it's a list, it says I can't elaborate the do notation. I don't know that R is a list since there's no way to resolve that union here is the list dot union. This was I forgot how many times you had to provide the argument. These are the type explicitly while developing Lean itself. It was super annoying. And now in Lean 4, you have this postpone resume approach that makes the system way more convenient to use, right? We don't need to provide the type of R. What happens here, it's going to postpone the elaboration. Even if it's deeply nested in a bunch of binders, it will be able to resume the operation. Just showing variants, how it can write in a nicer way. We support notation like F#. Now, another experiment was heterogeneous operators. In Lean 3, all the built-in plus times, they're all polymorphic homogeneous operators. Homogeneous mean that 2 arguments have the same type. The main frustration here is not about matrix multiplication, right? It's not homogeneous. There's also nest interaction with coercions. Like suppose that X is a net, I is int, I plus X works. Why it works? Because we start. Oh, I have alpha. Oh, alpha is an int. Then I get X. X is a net. I have a coercion from net to int. Oh, worked. Here doesn't work. X is a net. This way alpha is a net. Then I try to elaborate I is an int. Oh, there's no int to net error. For me, this was outrageous. Rust supports it, but I understand. Some people think this is a feature. I just saw a comment from Kevin saying, "Oh, this is amazing! This is a great feature." I mean, but yeah, okay, I understand. But for us, this is a bug. Let's try heterogeneous operators. The first attempt. Let's try make it heterogeneous. I'm just putting priority higher here to take over the plus. Now it's not the homogeneous anymore, it's my heterogeneous one. And the first roadblock is this one here. We have Y, you don't know the type of Y, this way you fail, because how can you synthesize the instance if you don't know the type of the second argument, right? It's an error. And come on, I don't want to provide the type of Y here. Okay, then come the missing feature. The missing feature, Haskell has something similar to that. Rust is a different way. It's not exactly a default instance. The feature we added is like the Haskell default instance feature. You can tag an instance when you have nothing else to be done. You finish elaboration, at least in a checkpoint. There's nothing else to be done. You can try this default instance. Here, basically, we are trying, oh, if you don't know, you have this heterogeneous plus, you don't know what to do, okay, use the default instance. Assume it's homogeneous. It's morally homogeneous if you don't know what the type of Y is. It's probably assume that's the type of X. And we have been very pleased. You can have matrix multiplication, right? The addition in matrices is homogeneous, but matrix multiplication is heterogeneous. You have it here. You can also have scalar matrix multiplication. You have an alpha multiplying by a matrix. Everything works. You see that I'm mixing the times here. This A is scalar matrix multiplication. Here's the heterogeneous matrix multiplication. Everything is smooth. But these are good points to show the scoped attributes you have in Link 4. Like I realize some people will not like this heterogeneous stuff. Saying nothing is written in stone, right? You can even have scoped. You can declare notation that's activated when you open the namespace. For instance, you can even have one step further. You can have homogeneous polymorphic. No, I want to have net op namespace that says plus is the net adds. It's not even the polymorphic homogeneous adds. It's the net adds. It's exactly net adds when I write plus. And you define this scoped notation in your net op namespace. Now we left net op namespace. You can use n plus I is heterogeneous one. It's the top level one, the built-in one. There's when you say open net op, you automatically switch to this notation here. It takes over. And n plus I now is an error because you're trying to add a net with an int. You can do it, right? So most of the features, one experiment we're going to suggest to you all before you try even porting is figure out what you want to do. Do you want to use homogeneous polymorphic arithmetic? Do you want to use heterogeneous? You want to keep controlling manually many different namespaces, like I have the algebra namespace, I have the real namespace, and you keep changing the meaning of the notation as you go. You can try all these different flavors. Another feature that we add is implicit lambdas. I see all the time the curse of the underscores. You see things like that in Link3. This adds with a bunch of underscores. It looks hideous. If you look at how Haskell, this is defined in Haskell in Link3, it looks hideous. You can try to work around using the double curly braces. That's very few people know how to use this stuff. I checked last night on Netflix. There are very few occurrences of the double curly braces. It's really confusing for the user. You have single curly braces, you have square brackets for the type class instance. Now you have double curly braces to avoid that problem. It's too much. Implicit lambdas solves this problem. You have only curly braces in the type classes. Lean will figure out how to add them the scores for you, all this stuff. I mean, and here's just how you can make it look even nicer. This is the final version in 4, how it will look like. It's much nicer. You don't need all these auxiliary functions, state pure. It looks like how it's defined in Haskell, right? We have unification hints. Tom Hales, I think, is in the audience. He make a big deal that he wants bundled. Also, another motivation to add unification hints is that people can, there are always some places where the unifier doesn't work. This is a way for you to fix something in the unification engine without having to implement your own extension. This is a canonical unification hint example. I'm running out of time, but just try. You have a bundled structure called magma, and you have the net magma, you have the product magma. You have two magmas, you can create the products of them. That's doing the pointwise multiplication. The big deal now is that you always get stuck in the unification with something saying you have some S that's a magma that you don't know. You know that the type is net. How come it's impossible to synthesize S, right? Link cannot come up. He doesn't know what you want, but you can give a hint saying whenever you are stuck in this kind of situation, try to unify S with the net magma. And you have chaining like in type classes. You are stuck in this kind of state where you have S.alpha is the product of beta and delta. That's the recipe. Use the product magma and create these problems recursively. And now you can, for in this example, we are going to apply this hint twice and this one once. This is something for experimentation. I like the type classes. I understand some people think, oh, for math, this is bad. Tom Hayes make a point. He prefers bundled. Yeah, if you try it. If you think this is the way to go for it. I mean, I love the type classes, but everything is in the eye of the beholder, right?
And I just very quickly say, Leo, you should not worry about going overtime. We'll listen to you as long as you want to talk.
Okay. What about the kernel? Same design philosophy, right? Minimalism, no termination checker in the kernel. We want to make sure that people can write external type checkers, right? That's how it's our response, right, to anything like, I don't trust you, I don't trust the system. Yes, I understand that. That's why any extension, any modification in the kernel, we didn't want to compromise that. The ability for someone to write external type checker that can double check everything they have done, that can print whatever they have done, right? This is something that we will not compromise. The foundation is still the calculus of inductive constructions. I keep insisting on that. No inconsistency has ever been reported to a Lean developer. And actually people ask, in numbers of lines, the Lean 4 kernel is smaller than Lean 3. You may say, how come? Well, when we start Lean 1, we want to support many different flavors of type theory, like prop could be predicativity. You may disable predicativity of prop. You can do this. You can have or this, inductive predicates will not support dependent elimination. There's so many flags that we experiment, but now we are over it. I mean, we committed to the kernel we want, and we could remove a bunch of this kind of stuff, support for homotope type theory, all this stuff. I think now, in retrospect, it's like one day I was talking with Andre Bauer, these things do not matter, right? right? The kernel is nothing, right? It's a monstrosity what you have on the top, right? To make everything work. For sure, having types or not having types is a big decision in the kernel. And if you decide to have types, your types have to be expressive enough to allow you to write what you want to write. But that's it. Okay, let's see what's changed. We put back support for mutual inductives. Link42 supported them. This is mutual inductives are well understood. It's the same foundation we use to justify Link. Peter Daiber, I don't know if that's how we pronounce his name, but he has a really nice article describing, justifying, showing what's a valid multi-inductive data type. And it's like when you're writing a paper, you can say, oh, yeah, we have these nested inductives. This is just a convenience. You can always write, if you have this nested inductive, you can always write that is the mutual inductive that we covered in the paper. Yeah, but yeah, it's just a convenience, but the world, improving programming language is all about convenience, right? So especially when you're programming, you really want the nested inductives. For mathematicians, I understand, I get it, you don't need this feature, but for programmers, you really want the nested inductives. And what we did, we had support for nested inductives. You say, oh, but now you don't have a really understood foundation. Well, what we're doing the kernel to check nested inductives is exactly that. We expanded it into a mutual and apply the same checkings, right? What we are getting, what's the extra sauce, right, that you can't get by writing the inductive compiler like we have in Link3? It's like in the inductive compiler, you have a lot of boilerplates mapping list expert to this auxiliary list expert. There's a bijection between them, but you don't get definitional equality there. It's like it's provably equal. It's a nightmare in practice. What you get extra here, you get the definitional equality, right? Another thing that some people will find that is debatable, we have basic support for all the basic net operations are short-circuited in the kernel now. It impacts performance, but it was not the main motivation. The main motivation was examples like this one, right? This is not far-fetched. The Galois guys had problems with that. We are going to have problems with that. It's like you have a type BV, this bit vector. You have BVN, BVM, returns BVN plus M. And here is going to be unary. You're going to get stack overflows because you're adding things in unary. If you're doing kernel reduction, then people say, oh, do the binary nets. Now you have the unary, you have the binary. Come on, nobody cares about everybody. Net operations, you short circuit them. And it is not going to impact on the complexity of external type checker. You can implement in Haskell. Haskell has a big number package. You can implement your type checker in Scala. Scala has a big number package. You implement, oh, I don't trust their big number packages. Write your own, verify yourself. That's our answer. Here is really being pragmatic. And it's really smooth now. This kind of problem, if you try this example, I think in Link3 doesn't even work. In Link4, super smooth. We're just short-circuiting the net operations in the kernel, right? When the kernel is reducing, net add is going to short-circuit. In principle, it's not giving any extra power. It's just performance, and the experience to the user is going to be smooth. Again, no inconsistency was ever detected. The goal here, even if one day people find inconsistency, is going to be a high priority for us. ITPs are not widely used today. The issue is not soundness, right? Soundness bugs were found in other systems. They are still useful. They were fixed. Same thing here, right? There are two kinds of bugs, conceptual and programming mistakes. Link is based on really well understood foundations. And if there's a conceptual bug in dependency type theory in CIC, very unlikely, in my point of view, to happen. Programming mistakes are easy to fix, right? That's the minimalism is our defense against conceptual bugs. Documentation, we have a lot of documentation already. We're still work in progress, but we are going to keep expanding as things get more stable, right? The documentation is written from the point of view of a computer scientist, right? I mean, if you want someone who wants to use Lean as a programming language, of course, you're free to write from the mathematician point. Maybe it's a different set of documents, but we have some documentation. There are many steps that we still need to do, right? So we have to finish well-formed recursion, auto-generated induction principles, have all the UI. I mean, we still have a lot of UI features missing, but the basic functionality is there. Sebastian is going to demo this stuff later today. We have missing tactics, diagnostic tools. For instance, we have traces that are structured. You can write programs that traverse the traces, but the trace messages we have right now are more for the debugging, for us understand what's wrong with Lean. Sometimes you want different sets of trace messages for you to understand why Simp is not working. You have a bunch of Simp rules, and can you see that difference? I mean, there are trace messages for understanding why there is a bug in Simp, and there are trace messages that are useful for understanding why your Simp lemmas are not doing what you want them to do, right? And this is something that you need experimentation, you need to help from users, right? There are many other features. I will not list them. I forgot to say, I put in the beginning this picture of the big mountain. That's how Sebastian and I feel when we see what has to be done in Lean. It's like a huge mountain. Sebastian sometimes jokes saying, "Oh, I don't even think about it." But I have one thing that he always tells me when I say, "Oh, let's do this part in Lean 2." He always comes back with these reassuring comments. Why not? How to contribute? I mean, the best way to contribute is with experiments. Try Lean, isolate issues. For instance, here is an example we have. It's called reads 1. Reads isolated this issue for us. It's really helpful when you have something that is this small and shows what is the problem. In Lean 4, this works thanks to reads. There's no reads 2. I mean, read disappears, but read 1 is there. I mean, and it was useful. This thing is super useful for us. Experiments, crafted benchmarks that reflects performance problems in MathLib are helpful. Experiments on homogeneous versus heterogeneous operators are helpful. Experimenting bundled versus unbundled, trying the unification hints, deciding what to do. I'm happy to discuss, to reserve 1-2 hours per week to discuss issues using Zoom. On Zulip, for me, doesn't work. I mean, this asynchrony is horrible. It's a time sink because you write and people come back 15 minutes later. It broke your concentration, right? I mean, Zoom, no, it's face-to-face, right? I'm willing to discuss. I mean, things face-to-face. Zoom, for me, Zulip, I don't like. Only technical stuff. With Sebastian, we use Zulip all the time, but we are in sync, right? What we want to do, right? Then people say, "Oh, I want to contribute to the Lean code base." Yeah, okay. There are many mismatches, different cultural backgrounds. I'm happy to collaborate and listen, but time is finite. We had many successful attempts of people contribute to the code base. It's never smooth. I try some funny, Daniel and I sometimes make jokes about this stuff, but they reflect exactly from our point of view how it is. We feel, Sebastian and I, we are climbing this gigantic mountain. It's a war. It's literally a war. It's tough. It's not fun. It's insane how painful it is. And sometimes people come with crazy stuff. I mean, no, if you want to participate, great. but has to come for real. It's not for having fun. I cannot guarantee fun. I can guarantee that I will pay attention. If anybody asks Sebastian, I usually respond immediately to anything he writes, unless I'm sleeping. But if you want to contribute, you have to come to help. We can't afford helping you or solving. Sometimes people want to do some crazy thing. Yeah, it's great, but we don't have time. Right? If you want to help, great, but you have to help what we are trying. We have our own research agenda, our own dreams, right? For instance, I'm going to give here an example of a successful contribution. For instance, the Galois Incorporation guys, they have been using Lean for a while. They are in the Lean 4 channel. He's a successful collaboration. Andrew Kent, we had the 4in. He wanted the parallel 4in, that you can traverse 2 collections in parallel. Yes, we know that Rust and Racket can do it, but it creates so many technical difficulties with termination. Right? You could try to do well-founded recursions. I'm like saying, Andrew, we tried that. We are not going to go through these routes. He said, okay, I'm going to try a prototype. He tried ideas, and he came up with a really cool idea that we have it's a hybrid approach where you have the main traversal, that's the Lean 4 approach that guarantees terminations like a fold. But for the other collections you're traversing in parallel, you use streams a la Rackets, right? He figured out the problem. One thing that helps, he talks our language. He's a computer scientist too. Then he showed to us what he has done. We integrate his ideas. Sebastian will polish some of the ideas. We integrated. It's next day it's working. When he comes on Monday, he sees that it's there. Everybody benefited. Right? He's happy. We are happy. Lean's better. I use this notation now when I'm implementing Lean. Right? This is an example of successful contribution. He knew what is feasible, what's not feasible, right? He tried hard the prototype. He tried different ideas. He has a notion what works, what doesn't, right? Thoughts of mathlib conversion. I want to finish with that. People ask, my advice, take everything with a grain of salt. I don't like to tell people what they should do. The same way I don't like when people tell me what my research agenda should be. But here's just some thoughts. Play with the system before trying anything serious, right? Try feasibility experiments. Try to identify what is a problem, right? People say it takes hours to compile mathlib. Daniel made some, maybe, of course, the experiments were from last year. Daniel conjectures that you can build mathlib in seconds or minutes if you use better indexing. You avoid the simp issue. It should not take hours, right? Trying to identify problems before you try a huge effort, right? Sometimes just suffering unnecessarily, right? Then the other question, you keep Lean 4 keep changing. Is Lean 4 a product? Yeah, there's no spec. We are trying ideas. I can't guarantee to you that we will not keep changing. We will not have to keep modifying. I don't have a good answer for that. An approach, if I were in your position, if I had this big library and I want to port with math to Lean 4, what I would do, that I can tell you. I would try to extend the export mechanism in Lean 3 to export metadata like class instance information, notation, and anything that's relevant to mathlib, right? Then I would try to write a tool that imports this data in Lean 4. Then I would try to set up a build system that we can have Lean 3 and Lean 4 files to coexist in the same project, right? Yeah, some people would continue in Lean 3 because they like Lean 3. Some people would try Lean 4. They would start seeing benefits. Maybe people would switch smoothly. You may ask, oh, can you write that? No, I don't. I'm overwhelmed. I can't. This takes a lot of effort to write this stuff. I can help talking if you on Zoom about this stuff, but someone needs to do that. Well, someone needs to do. Needs is a strong word. That's what I would try to do if I were in your position. Projects in our radar, right? You have custom automation to the Imogan challenge that Daniel started. This Gantt challenge, we want to use Lean4 for that. A colleague of mine, Oli, he said that he's going to be later, or maybe he's already here to talk. He has plans to use Lean in high performance computing to do intensive computations. He's looking for interns, people that can help him use Lean in his project to do high performance computing. We are interested in anybody that's interested, seriously interested in integrating Lean with setting SMT solvers, people that are interested in integrating Lean with Rust, building GSLs on top of Lean. These are projects that we would also collaborate. We would be eager to collaborate. Conclusion, we implemented Lean4 in Lean. It's a very extensible system. It's a real programming language now, but we didn't compromise logical consistency. It generates C codes. You can mix compiled and interpreted codes, right? You can, maybe on Wednesday, we are going to talk about the plugins that you can write your package, generates a dynamic library with C. You compile the C code into a dynamic library and you import in Lean. We're going to show how to do that, but you can extend Lean. You can actually, in principle, build a Lean that's completely different from the Lean we use. You can define your own category, syntax categories, your own elaborators. Nothing is fixed, right? You can have a mathlib language that is very different from the Lean4 language that we use to build Lean. We understand we are computer scientists. We are going to have a bias towards the way computer scientists do things, but it doesn't need to be the same. And you are free now to do how you think is best, right? Sebastian now is going to, he has some really cool demos on the package manager he's built using Nix. Sebastian, are you there? Sebastian?
Yes, I'm here.
Okay, okay, great. I'm going to stop sharing. You take over. Okay.
Okay. Yeah, I'll try that. Ah, that's the way. Okay. Is this working? Can you see my slides?
I can see demo.
Yes.
Okay, great. All right. So, yeah. You've already heard about all the great language features in Lean4 from Leo. So what I want to do as a conclusion here is just to give you a quick peek at what the user experience of Lean4, like of this current milestone release, actually looks like in practice, without going into any details. But speaking of user experience, I actually first want to talk about how users can get to that part, how they could set up Lean for now and in the future. And so if we review the state of setting up Lean3, there's quite a few components involved. Like at the core, there's the Lean executable, which comes with the Lean package manager. And those are distributed via GitHub releases. But actually, I assume that by now, most users are not, in fact, downloading these releases by hand, but are using the Elan Lean version manager to download exactly the correct version of Lean that is encoded in your project configuration. And yeah, so Elan is usually installed via this famous curl pipe sh mechanism. So that's another part that is not part of the actual Lean distribution. And yeah, we're not finished yet by far setting up Lean3. So Patrick has already mentioned his Lean project tool, which can be used to download these Lean tarballs from mathlibs.ai and so on. And just to keep things interesting, this is distributed via yet another mechanism as a Python program. And after that, you can actually start installing or using your favorite editor and finding the correct Lean extension for that, which hopefully will then be able to actually find the Lean executable on your system. So yeah, these are very many moving parts involved, and I think we've seen on Zulip that anything that can go wrong here in any step of this will in fact go wrong for someone on some system, some distribution using some configuration. So this will only get harder, in fact, when people start using the advanced features of Lean 4, like, as Leo mentioned, compiling Lean 4 code into a native binary. Well, you'll have to have a C compiler for that in your environment. And maybe furthermore, you want to link against some external library using the foreign function interface. Yeah, well, I guess you better tell your users how exactly to install that external library on each single distribution using the different names they use and so on. And so maybe you think here that, well, I don't care about any of this. I just want to do proofs. Okay, but you're probably still interested in doing proofs fast. And then what Leo mentioned is that you can compile your tactics or the tactics someone else has written, the ones that really the heavy ones, into native code and then load them back into the Lean executable as plugins to use the native compilation so that they are actually fast. But yeah, you or someone else has to compile that and somehow get to your machine. So yeah, there is a lot to orchestrate here, and yeah, it is even more to orchestrate in Lean 4. And it's certainly possible for like every platform to write, I don't know, a script or something that more or less robustly sets that up. But so the one thing I'm sure about is that I don't want to be the one to write any of this. And yeah, I assume that most of you feel the same, that frankly, we have more interesting stuff to work on than like setting up infrastructure. So this begs the question, can't someone else do this for us, or has already written some system that we can use for this? And so in the last year, I've become more and more convinced that, let's say, at least one possible solution to this issue is called Nix. Nix is a purely functional build system and package manager, and I could probably talk half an hour in depth about Nix at this point. But yeah, I try to make it short. And let's just say purely functional here means much like in Lean itself, that building with Nix is a pure function taking inputs like build recipes, let's call them, and translating them to an output. And it will always be the same output given the same inputs, regardless on what machine with external software and so on configured and installed. So because Nix can give this reproducible environment, it also becomes quite simple to share these outputs via the cloud, via the internet, much like Lean project does, but I mean in much general way. And well, yeah, if you really want to, you could also, by the same token, use Nix to build your project like in a massively distributed way in case you have a few, I don't know, spare university machines lying around or something. And in the end, because Nix recipes cannot depend on external software, but only other Nix recipes, it has in fact become the largest software repository in the world by this point. So yeah, if you do want to link against some obscure library from your Lean 4 code, it will most likely already be packaged in Nix, at least for the systems that Nix actually supports. So this these are all Unix-like systems, so Windows is not supported by Nix. You would have to use the Windows subsystem for Linux to run Nix on Windows, which I think is getting more and more popular with Windows developers. But I acknowledge the limitation that you might, for example, not have sufficient permission to install WSL on, say, a university machine for some course. So that is a potential issue for using Nix in practice. Okay, given these restrictions, since we've been talking about experiments today, this is the experiment I'm proposing today, which is to build and evaluate a Lean setup, a way of setting up Lean purely based on Nix. And yeah, I actually have a working prototype for that. So I've basically taught Nix how to build a single .lean file into the corresponding .olean file and the .c file as well, which then again is compiled using some pinned C compiler into a .o object file. And all of this is cached in the local Nix cache on your machine, and optionally can also be shared remotely with other people. And yeah, you do also get a perfectly reproducible development setup out of that other people working on the same project can use. So, so the remote caching you already know from Lean project. That's, yeah, I mean, at least for the current state of the mathlib, that's like a mandatory feature. But actually, there's a big difference in here in the granularity. While Lean project, at least as far as I know, works on commits. Here I'm working actually on the file level. So even if you diverged from upstream, you can still use the upstream remote cache. Nix will automatically try to reuse the build results from those files that you share with upstream, even if you're on a completely different commit. Like, it does not care about the actual commit hash at all. And because it also does that locally, it means that even when you change branches, you keep that progress, you don't lose it at all. And at some point when you switch back from the branch, your build will finish instantly, because Nix is still remembering the previous build in its cache, at least until you at some point call the Nix garbage collector. And if you want to get real fancy, you could also, like, you could even change branches while doing the build without corrupting it. And you could even build a commit without checking it out, without even checking the repo out, just pass the URL and the commit hash to Nix. So yeah, we've set up a Nix binary cache for the Lean for repository using the caching service, which gives you 10 GB of storage for free for open source projects. And our CI is already feeding that cache and also using it itself. So say on the right-hand side, if we have a minor like markdown change, the build step will actually constitute only of downloading the previous build of Lean, which is still a bit slow here with 3 minutes. Could probably be optimized, but especially the test part, the test step after that, finishes immediately, because that too is now a Nix recipe, and we push the result of that to the cache. So Nix will immediately notice here that these tests on this input, which does not include the markdown file, has already have already succeeded. Okay, so it is working, but it's still very much experimental. I have to say that, in part because it's actually using an unreleased build of Nix to do all this stuff. So yeah, maybe not quite intended for general consumption yet. So if you're interested in this stuff, there's definitely some open questions to resolve, to discuss and work on, like, yeah, without going into too much detail, like does this actually scale to, I don't know, thousands of files over dozens of Lean projects. Yeah, in the end, is it actually simpler to use, or is, I don't know, maybe setting up Nix just as bad, just as brittle as setting up all these other tools in the, let's say, call it the basic setup? And if it is worth it, but if we do still have users also using the regular Lean package, how will these two worlds cooperate? For example, do we have a Nix config and a Lean package.toml in the same repository, or can we somehow unify that? So yeah, many questions left to be solved. But for now, let's move on to the actual demo. Okay, so I hope you can now see my terminal. I assume that's a yes.
Yes.
Great.
Yep,
Yeah.
all good.
Yes.
Okay. Yeah. Thanks. Okay, so let's assume we have some Lean package here, and I just checked that out, and I now want to work on it. So it has the Lean package.toml. I could now use Lean package and install all this other stuff, but let's try to use Nix here. So we tell Nix to run VS Code, let's say, on the current project, which is the dot in the front, and we want to then open our lone Lean file. Okay, and off it goes, I hope. It's a bit slower than before. Let's hope it's not too slow. Okay, so what is happening right now is that not only is it downloading the exact Lean version from the Nix config and then querying every single Lean file to check if it's already built from your dependencies, which in this case is only the Lean standard library, but it's also downloading VS Code, like a pinned version of VS Code tested with this version of Lean, as well as the Lean extension for it. And then in the end, it will actually compose all of that into a working Lean development environment, which hopefully should open very much soon. Okay, great. Yeah, so there is actually, as Leo said, our whole language server is still pretty new. So there's not too much to show off here, actually. But, well, we can, for example, see that there is basic error reporting and immediate incremental compilation. On the right-hand side, you can see that this generated some further errors further down. And maybe you saw that there is at least one nice new feature here compared to Lean 3, which is that up here, we actually now have this breadcrumb bar telling us the namespaces we're in for the first time without having to scroll through the file. And I can, in fact, click on that to navigate through the file. And I can also open this the search bar for searching by symbol, for example, for at least in the current file for now. And yeah, this just shows you what we can now do with our new parser that generates an actual concrete syntax tree. And yeah, all the stuff we can now finally access simply from Lean code, since the language server itself is written in Lean, because yeah, most other stuff is now written in Lean as well. And so we can access formerly hidden data. Yeah, and that's really it for the demo. So I think if we do have still time left, I guess we can now move to Q&A. I don't have the schedule in my mind right now.
First, I think we owe Leo and Sebastian a huge round of applause. Thank you guys so much for this wonderful presentation and unbelievable yeah, this is really fantastic. Thank you guys. The official schedule says that we had Q&A and then a discussion about porting mathlib, but I think we've had so much to listen to that we're going to postpone the porting mathlib discussion. We can do that asynchronous, on Zulip, whatever. That is no big deal. So yeah, we have time for Q&A. My guess is there are going to be a lot of questions. I've seen some in the chat already. There's one from Cyril, one from Simone a while back. Maybe, yeah, Cyril, Simone, did either of you still have a question? I've now lost in the chat where that was.
I think Cyril's question was whether unification hints can depend on like type class problems.
In principle, yes, but we never tried. A header is a header as any other, right? We have parameters there. Some of them can be type classes. Yeah, in principle, should work.
And the other one,
would like to try that.
Yeah, and the other one I think was some. Oh yeah, Simon asked why we brought back unification hints in the first place.
At one point, I was debugging an issue with one of the Galois incorporation. They posted something that was an issue on the type checker. The unifier was failing to unify something. In that example, you could put some, let's put another hack inside of the unifier to handle their case, or you could add unification hints, right? The problem they had could be solved using unification hints. Another motivation was Tom Hales was making a big point about having bundled structures. You need unification hints for that. Another thing that was after we finished moving to the new front end was not a big deal to do the unification hints. It's actually small, the piece of code. It was also an experiment to see if people want to do it. What would it take for someone to do that? I mean, was like customizing the unifier. Yeah, it was a mixture of experiments, avoiding more hacks in the unifier, Tom Hales ranting against the type classes. It was a combination of things.
Gabriel, you had also asked at some point in the chat about Nix versus using Ninja. I'm not sure if that question is still relevant. I'm doing a bad job chairing this session because I didn't write down the actual questions. I just wrote down names. I'm sorry.
Okay, so let me just ask this again. So I mean, whenever I've used Nix, I mean, there's always like this like big startup delay when building one derivation. So I mean, I'm just wondering, how do you feel it's much slower to use Nix to build every file separately, or can you quantify this? Do you think it's gonna get better?
Right. Yes, that actually was a big problem when I first looked at Nix. But I'm not sure if you're familiar with the whole flakes stuff. That, like, the issue you're mentioning, that is actually like the biggest reason I'm using this pre-release Nix version, because it does now have a cache, an evaluation cache. That means you don't have to evaluate the half of Nix packages every time you launch a build. Yeah. It could still be much better. Like right now, it's only basically only caching on the top level. So if you do change something, it will remove that cache even if you didn't change Clang itself. So it will reevaluate the Clang derivation. But yeah, it's already much better. And really, this was the part where I really started evaluating Nix, using Nix for certain. And I think last time last time I measured, I think if you build the whole standard library of Lean with Nix, there's like a 4% overhead or something. Yeah, there is definitely like some constant overhead still. or from like initial setup or something. But that's so small that it usually doesn't matter, especially now that we have the language server, that we're not like running nix on every single change.
Right.
But yeah, that's also something that definitely has to be experimented with, like what's the performance impact of nix.
So I have a question about the paper on hygienity. I'm kind of like skimming it right now and see the definition of syntax could also be missing. So I mean, I know this is kind of like a really hard problem with the general macro, because I mean I'm used to Racket, and I know that like error recovery is really hard to get right, and so I'm not sure how you are dealing with it, and if this is something that can be ported back to, say, Racket to deal with, you know, the error recovery, syntax error recovery.
I'm not sure what's the connection between macros and error recovery. Like that's just something that's happening in the parser before expansion, right? And I also don't know how error recovery works in Racket. Or do you mean something other than syntactic recovery?
I mean, it just fails, right? I mean, when it fails to expand something.
Okay. So error during expansion.
Right.
Right.
I'm talking about the expansion.
Yes. So that's definitely interesting. Like, how do you debug a macro? And yeah, that's tons of prior research in Racket, and also practically you have this what do you call it, like a macro debugger in Racket. That's definitely something we should probably have at some point. Right now it's quite simple. Like yeah, by default it will show you errors on syntax. If the syntax is still part of like the original one you wrote in the file, it will show the error at that position. If it's syntax that has been introduced by a macro, it will show you the error at the point, like at the top level part where the first macro was expanded. But we do also have an additional option, basically a trace option that says, give me the whole macro stack on an error. That's off by default, and that's usually fair. But yeah, if you need to debug a macro issue, you probably want to toggle that on. But yeah, we could definitely do more user interface stuff there.
Thanks.
There's a question from Simone about writing tactics and theorems in the same file.
Yes. Right now, what's going to happen is interpreted. The tactic is going to be interpreted, but Joe Hendricks tried experiments on putting Clang inside of Lean to compile dynamically the code. We didn't want this option initially because it would make Lean more complicated to build, because you would have to depend on Clang. That's a huge project too, right? But now with Nix, right, Sebastian has this Nix build system for Lean. It makes it really convenient for having to taking as many dependencies as you want. So this is something that we definitely want to revisit in the future, to take a dependency from Clang, and now you can have your tactics, even if they're in the same file, they're going to be compiled on just in time, and you're going to use the binary versions, right? Right now, if you want performance, you have to create a plugin and import, right? The plugin.
There's a question from I think it's Carl Pamskag about multi-threading and parallelism in the chat. Carl, did you want to ask it, or should we read it?
I mean, I can ask it. Yeah. So I mean,
Thanks.
it's just asking about like there is a section in the manual about multi-threading, but I don't think it's kind of in a to-do state. So I was just wondering about how parallelism multi-threading compares to maybe Lean 3 Is it like fine grain? Can you get sort of parallelism at the proof level? Can you avoid proofs and things like that?
Yeah, this is one thing that we have tasks like in Lean 4 too. You can program using tasks. Actually, the Lean server was implemented using these features, right? But compiling terms in parallel, like we had in Lean 3, we removed this feature. This is like increase a lot the complexity of the design, puts limitations on what you can do on terms. But terms now are fundamentally different from definitions. It doesn't help much. For interactive use is zero improvements, because what you really want in interactive use is incrementality, is not parallelism. For building parallel, even that we measure is almost insignificant, the advantage of building theorems in parallel. The file level parallelism is more than enough, right? We discussed this stuff too many times, right? The complexity doesn't pay off.
Okay, thank you.
I missed a question from before, sorry, from Tom Houlet, who asked about the VS Code Lean 4 extension. Is everything necessary exposed, or does it require extra work? Yeah,
I think that too. We are not exposing the technical. This is actually not the hard part is to this in the server side, but we are not exposing right now. We are not storing the technical intermediate states, type information, or all this information is not a big deal on the elaborator side, but it's a lot of work. I don't really understand how the server works. When Jack and Mark probably and Sebastian can explain. As far as I understand, it's a lot. They're going to have to do extra work there to make this a reality. But this is the plan.
I see.
Right.
I know that the VS Code extension only exists as of very recently, right? So yeah, certainly work in progress. Mario, you have a question there. Yes.
Yeah, so I was wondering whether you'd considered targeting LLVM instead of C, and whether there might be any benefits to doing that because of all the annotations that you can add.
Yes, we considered. The first reason was the same for having tactics in terms in the same file, right? So we'll take a dependency on LLVM, would make Lean even harder to compile if you are a user that's downloading the sources and compiling. People complain about that, how complicated it is. If you put LLVM, wow, the complexity is way higher, right? So you have to be a hardcore developer to do it, hardcore user. But now we're going to reconsider again, right? As I said in the previous one, tactic versus with terms in the same file. Now with the Nix setup that Sebastian has, we can take dependencies. It's going to be super smooth to install Lean, even if you have LLVM as a dependency. There are immediate benefits. One of them is the just-in-time. We can use the JIT engine in LLVM, although you don't need to target. I mean, as I said, the experiment Joe Hendricks did, you don't need to map to LLVM IR to be able to use the JIT. I mean, he showed that. He managed to show an example where he gets the C code, regenerates, compiles using Clang, goes to LLVM IR, use the JIT engine, and it works, right? This is a really nice first milestone, right? It would give users the capability of compiling the tactics in the same file, use a compiled version of the tactic in the same file they define the tactic. Next step would be, yes, mapping to LLVM IR would benefit things like being able to control, putting, as we move forward, debugging information, having better control. For instance, we handle tail call optimization for self tail call, right? So you have a function F that calls itself in the tail. We do a go-to instead of but if you have a set of mutually recursive functions with tail calls, to be sure as a tail call, it would be much better to go to LLVM IR, right? Otherwise, you have to pray that the C compiler is going to do something smart there. There's no guarantee, right?
When you say that you have to take a dependency on LLVM, don't you already have to take a dependency on a C compiler in order to because you're targeting C at this point, right?
Oh yeah, but it's much. People install independently, right? So when you take a dependency file out of VM, is that you have to be that dependency, that version. There are mismatches between the versions. The C compiler is stable, right? So you can change the compiler, but the language, the C language is stable, right? LLVM is not stable as a C language, right? And we can use GCC or Clang. On Windows, you can use the Visual Studio compiler. It's much more pleasant, right? Things are much more stable. LLVM is a moving target. It's like Lean and MathLib. If you take a dependency on LLVM, it's the same thing, right? They keep changing. We have to keep adapting, and people have to get the right version. It's more complicated. But with Nix, is going to change, right? I mean, this efforts was a nice experiment that Sebastian has done. It's really impressive, the build system, what it can do, right, for you.
There's a question from Joe Hendricks about concurrent programs. Joe, you're here.
Yeah, I heard kind of the topic of concurrency, and I had some questions about if the Lean 4 runtime had any issues with supporting concurrency, and if you had thoughts of whether that should be in the standard library or something that the community should address through a separate package.
Yeah, we have tasks, right? And we have tasks of high priority that are essentially threads, right? What else is okay? This is the basic support we have. What's missing? Like new tags, right? Probably we don't have new tags. Probably you would want to have these channels Haskell provides, right? We want to add them eventually. Yeah, but we have basic support for parallelism right now. But there are still some features that are missing, but the basics is there.
Okay, thanks. I'll have to use it.
And they have to be, in fact, built in, at least the primitives, because, for example, when you spawn off a task, we have to mark all the objects in the closure of the task as multi-threaded, which is like one of these optimizations we have in our reference counting system, that there's a difference between single-threaded and multi-threaded objects. So probably like those primitives will not be able to be provided by the community.
I see a question from Adrian about the planned SMT solver integration.
Oh, there is no plan. I was hoping someone's going to step up.
That's what I thought.
What I mentioned on the radar is like, if someone wants to do it, yes, we are going to listen. We're going to try to help. We're going to work with you. Of course, if it's not a serious effort, we're going to bail out. But if it's a serious effort, we will try to help.
Can I elaborate a bit? So, well, I would be interested in SMT solver integration, but I'm just not sure how useful it would be to mathematicians who are interested in things like the theory of rings, because SMT solvers, well, I don't know much about them, but they seem to be optimized towards programming.
Yeah, I can tell you that I would be interested in SMT, right? I think they, for instance, as I mentioned, my previous system was E3. One thing I noticed that we did a layer on top of Python, and people built many things using this layer, right? Because it has its convenience, right? With Lean, you have extensible syntax. You can have GSLs. You can implement your own state machine verifiers. You can do protocol verification. You can do a lot of stuff on top of SMT solvers, right? You can write GSLs for solving puzzles, GSLs for verifying some, for instance, Verilog or something like that. There are so many opportunities for verifying protocols, verifying state machines, and so on. It's a quite different area, but you could view like instead of having Python on top of Z3, you could have Lean on top of other SMT solvers with tactics, with preprocessing, everything available to users, right?
Patrick asks about the possibility of having widgets as an edstock, which, I mean, in my mind means something about hooking into the server interface from within Lean code, but I don't really know how that would be architected.
Yeah, I think there was a short discussion on Sulib about that. I'd have to look that up. Yeah, I think the best idea would be to have that pluggable into Lean without having to edit the Lean repository itself, especially when it is still a bit experimental. Yeah, so I think these kind of what are the extension hooks we need to provide to enable other people to implement cool stuff for Lean. That's also something, yeah, we need to find out in the near future.
Yeah, I mean, in Lean 3, Ed had to modify the Lean 3. I mean, this is part of what happened in the community for Lean 3. So yes, the question was really about how would that work in Lean 4 without messing up anything you do on your side, and stuff like that. Yeah. Hooks and everything.
So a question from Enrico about incremental checking of Lean files.
Well, it's very similar to the idea in Lean 3. You have checkpoints, right? This Lean server continues from a checkpoint. It's dramatic, the difference. After we check and Mark did that, first we have files that are implement very big functions, right? Functions with many mutually recursive functions, with a lot of macros going on behind the scenes. Our compiler has a performance problem when he unfolds too much, inline too much. You get a code explosion. I have a file that's like 10 seconds to compile, right? And it was annoying, right? So you type something, 10 seconds later, you get the feedback, right? As soon as Mark and Wojciech finished the Lean servers, Sebastian integrated, wow, it's night and day. It's instantaneous. I click, boom, you get exactly the error. Or the error goes away immediately because it's getting the checkpoints. Yeah, but that's the same idea of maybe there's some improvements that I'm not aware.
There is one significant improvement actually using our new parser. So I'm not sure if you guys ever noticed that in Lean 3 is that if you edit a command, wait, I should be careful about this one, but if you edit it, it should also reparse and reprocess the command above it. Because the issue is that if you say like you're on a def and you actually delete the E out of the keyword def, that makes it not a command anymore. It actually makes it a function call to a function diff in the command above. And that means that we always had to process more than we would like to in Lean 3. And now with Lean 4, correct me if I'm wrong, what we do is, well, we still reparse the thing before it, but if that command, if the syntax tree is exactly the same as before, then we know that the previous command has not changed. I think I went wrong somewhere in there, but yeah, we do diff syntax trees now. And I think we can also, going forward, we could do even more interesting stuff. Like if you only inserted a new line, we could just shift all the errors below without actually reprocessing anything. Or if you just edited a comment and so on. Like the sky's the limit, what we can do with the syntax trees.
So we're nearing the end of our Q&A time. There's one more question at the bottom of the chat that I already see a +1 for it. I'm curious too. So Patrick's asking about caching state inside of a long tactic proof.
We have been talking about this stuff a lot.
Yeah.
The initial plan was saying, okay, we have deeply nested statistics. It's a nightmare to cache these things. We will never be perfect. We say, okay, let's try to do top level proofs. You have imagine a begin ends. You have a sequence. This one we can do now, right? But nowadays we have now these structured proofs, right? That shall not really change anymore of commands. It's the same problem, right? You can have this structure that you keep going deep inside. Same issue. Then we start discussing, oh, maybe we should cache specific statistics like Simp, right? When we talk about, Daniel was the first one to bring this stuff up to us in Link 2. I think he was using Link 2. Was a nightmare for him because he was relying a lot on Simp. Clement from Cork has the same point, saying, oh, look, I have the statics that applies Cork Simp, not Link Simp. That's doing like, it's our G-Simp that keeps unfolding a lot of stuff and takes seconds, right? And so caching would be essential. After all, a bunch of discussions, we think the first step would be to focus on Simp, right? Or tactics like Simp. Try to cache them. It's like one idea we had is like we create a lemma. The same way you have abstracting link tree that you can extract, you do that, right? And then the cache is telling the lemma you should apply there. And you check if the term that you create can still be added to the logical context, check if you can solve the goal by applying it, really minimizing the dependencies on the current state, right? That's one thing, yeah, but still all in flux. We want to address this problem, but the original plan we had, it doesn't really work because of our nested, we have a structured static language now is going to create the same problems you had in Link 3, right? With nested beginning end blocks in terms.
It's nice to hear that it's on your minds at all, to be honest. Like that's I mean, the state of the art is that there's no caching, and we've made do with that in Link 3. So any improvement is huge.
Already, if we use the half tactic and state some intermediate claim and prove it, if that would be cached, that would already be an improvement.
Yes. Cool. Yeah, it's a good thing to keep in mind. I mean, yeah, if they have is already, this is even easier. We discussed other ideas like saying, oh, we have a mode that doesn't guarantee reproducibility, but it's good for interactive use. What it means is like, you may succeed because you're using a cache, but when you try to replay without the cache, it doesn't replay. But maybe this, if it replays 99.9999% of the time, this is good enough. We discuss ideas like that, imperfect cache. Yeah, well, we can start. I think it's a good point. We can start with the have. To have a have that caches, and you can even use it if you have this have with support for cache. You can even create a simp macro that expands into a have. Mm-hmm. That calls Simp, right? And you can keep improving from there.
Great.
Yeah, so I would suggest that we now move to the social hour, the workshop dinner, quote unquote, on Wonder, which is hopefully working again. But first, we should give Leo and Sebastian another big thank you. This is really exciting stuff. I imagine there are going to be a lot of people downloading and trying out Lean 4 and Nix, for that matter, over the next few days. So yeah, so fingers crossed that Wonder is working again. If not, watch Zulip and we'll try to create another room, or maybe the whole thing is down, but we'll find